Okay, so we know that when we run a current through a wire, a magnetic field gets set up around that wire. And we've also looked at how we can use a magnetic field to induce a current in a conductor. Now we're going to further our understanding of electromagnetic induction by covering what's called Lenz's law. So here we go. So when a conductor is exposed to a change in magnetic flux, an EMF is induced in the circuit. To generate electricity, we have to have a changing flux. If we take a loop of wire and we move it through or rotate it in a magnetic field, we can get this changing flux and induce an EMF. Another way to think about this then is that when the number of lines of force in a conductor is constant, then no EMF is induced. If we can change the lines of force, then we can induce an EMF. The instantaneous EMF of a circuit has this definition. So the instantaneous EMF that's induced in a circuit is equal to the rate of change of magnetic flux through that circuit. And so we have this equation here for our induced EMF, where here is our change in flux, here is our time. As we can see, if we can change the flux faster, we're going to get a greater EMF. The minus sign in this equation is just a reminder that the moving electrons create their own magnetic field. Okay, so remember, currents will create their own magnetic field. So this field then is going to be in the opposite direction to the magnetic field that causes the flux. This is called Lenz's law. Lenz's law says that the polarity of the induced EMF produces a current whose magnetic field opposes the field that induced the current in the first place. For example, say we take a copper ring and we drop it through a magnetic field. Before the ring enters that field, there's no current in that ring because there's no changing flux. Once the ring starts to enter the field, it experiences a change of magnetic flux and an EMF is induced, giving us a current. Now, as this ring enters this field, that magnetic field that it enters into is increasing, okay? This gives us a counterclockwise current in that ring. Once the ring's in the field, though, there's no changing magnetic field, so there's no current, there's no EMF, and there's no current. When the ring falls out of that magnetic field, the magnetic field is decreasing, so again we have a changing flux, but now it's in the opposite direction, and so that we get a current in that ring in the opposite direction. What Lenz's law tells us is that in these points, when there's an induced current in that ring, that current will set up its own magnetic field that opposes the direction of the original magnetic field. A good demonstration of this is taking a copper tube and a magnet and dropping that magnet through that copper tube. Now, copper on its own is not magnetic. A magnet's not going to stick to a copper tube. But when we drop that magnet through, it falls very slowly. Looking down from above, you can see that that magnet is not scraping the sides of that tube at all, so it's not like it's friction or anything that slows it down. It actually slows it down by several seconds beyond what you would expect it to fall. So what's going on here? Well, this is ultimately a demonstration of Faraday's and Lenz's law. Let's start by looking at just the original magnet. The magnet has its own magnetic field, which we can see in this picture here as these circles. Okay, so this is the magnetic field of the magnet falling through the copper tube. As it falls, the magnetic field of the magnet in the copper tube changes when you're looking at the perspective of the copper tube itself. This variation in the magnetic field induces electric current as predicted by Faraday's law. Faraday's law states that any change in the magnetic environment of a conductor will cause a voltage to be induced in that conductor. This induced voltage then creates a current in the copper tube that we call eddy currents, as shown here. They're called eddy currents due to the circular motion that they undergo. Now, because all electrical currents produce their own magnetic fields, these eddy currents produce a magnetic field as illustrated by these green circles here. It's Lenz's law that predicts the direction these induced currents and their magnetic fields will flow. Lenz's law states that When an electromagnetic field is generated by a change in magnetic flux, according to Faraday's law, the polarity of the induced electromagnetic field is such that it produces a current whose magnetic field opposes the change which produced it. Essentially, this means that the magnetic field created by the eddy currents oppose the magnetic field created by the falling magnet. It's the opposition of these two magnetic fields working against each other which slows the fall of the magnet. So, an upward force is generated that slows the magnet down and ends up taking a really long time for it to fall through the pipe. Okay, so let's look at a common situation where we can use Faraday's and Lenz's law to solve a problem. A rectangular loop is pulled through a uniform magnetic field at a constant velocity. This loop is initially outside the field, then it's pulled into and through the field and ends up on the other side of that magnetic field. So an EMF is going to be induced as the loop enters the field and as it leaves the field, since in those cases the flux will be changing. The flux is given to us by BA, the EMF is given to us by flux over time. Now for an EMF to be induced, the flux must be changing, which means that either the field must change or the area of the loop must change. In this example here, the area is changing as the loop enters the field, so an EMF will be induced. But once the loop is completely in the field, the flux doesn't change, so there's going to be no induced EMF. As the loop leaves the field, the area is again changing. It's getting smaller in that case, so once again there will be a changing flux, so EMF is induced again. The area of the loop is a function of the x position of the thing, since it's moving, which is determined by the velocity. Now the width here we're calling L, D is the full length of the conductor, and X here is the amount that is in that magnetic field. So the area of the part that's in the magnetic field would be length times the L times X. The velocity of the thing, it's a constant velocity, so we use our constant velocity equation. So X is equal to V times T. When we plug in the value for X into the area of the flux in the flux equation, we get BLVT. And LVT is just the area of the loop that's in the field. Because flux is the field strength of the field times the area, then we can plug that into this equation here for our flux, and we end up with this right here. In its final form, we drop that minus sign, and we end up with this equation right here, which is what you'd have on the AP test. And here we see that the flux is initially zero. Once the leading edge of the loop enters the field, that magnetic flux begins to increase. And since we have a changing flux, we're going to have an EMF induced. The maximum value of the EMF is equal to BLV. Once that loop is entirely within the field, the flux is no longer changing, so the EMF falls to zero. Finally, the loop begins to leave the field. At this point, the flux changes, and again, the area is getting smaller, so once again, an EMF is induced. This takes place until the loop's completely out of the field. At this point, the EMF is zero. So the flux begins at zero, gradually increases to a maximum value of BLVT. Once the entire loop is in the field, the flux does not change, it stays at that maximum value. It then begins to drop off as the loop leaves the field. The EMF changes from a negative to positive because the change in flux goes from positive to negative. Now the direction of the current in this loop can be found by using a right-hand rule and Lenz's law. Now our right-hand rule in this situation is only slightly changed, it's a little bit different. When we were doing a right-hand rule with charges, right, we put our thumb in the direction of the V, the velocity of the charge moving into the field. Well, in this case, we're going to still move it in the direction of V, but we basically say this is the direction of motion of whatever rail is moving through this magnetic field. The finger then still points in the B, in the direction of the magnetic field, and the middle finger now points into the direction of the current. So let's take this and figure out the direction of the induced current in this rail situation that we were just looking at. Okay, so here's the situation. Our rail is moving through this magnetic field this direction from left to right, And we're going to use our right hand rule, put the thumb in the direction of motion, which is the V, put the finger in the direction of the magnetic field, the B, which is into the page, and the middle finger will point into in the direction of the current through this thing. So when we do that, we put our thumb in the V, put B into the field, like that. F is pointing straight up, or rather I is pointing straight up. This time that's our current. So our current in this rail, in this front leading edge of this rail, is this direction from bottom to top. The direction of the current is up. So at the beginning, when the forward edge enters the field, the current will be counterclockwise. Current is induced only in that leading edge. The trailing edge is outside the field, and so no EMF is induced since it isn't in the magnetic field and no lines of force pass through it. The top and bottom cut through the lines of force, so no EMF is induced in them either. Once the loop is fully within the field, there will be no current induced as the flux is constant. There is no change in the number of lines of force cutting through that loop in that case. When the leading edge leaves the field, the flux will change because the area is changing, it's getting smaller, and so EMF will be induced in the trailing edge. As that loop leaves, though, the current direction is still going to be in the same direction. It's still going to be up. Nothing has changed, the right-hand rule-wise, which means that the current changes from counterclockwise to clockwise. Just to illustrate that, I mean, here's the loop leaving that magnetic field. By right-hand rule, it's still moving in the left to right direction, so the thumb is pointed in the same place. The B is still into the page, F still pointing up, which shows us that the current now is moving this direction, changes to be moving clockwise. Another interesting type of problem that you'll be expected to deal with is a moving solid rail problem. In these problems, you have two conducting rails that lie parallel to each other. One end of each rail is connected to the other with some kind of load over here, a resistor or a light bulb or something like that. A conducting bar is placed on top of the rails and is pulled at a constant speed across the top of the rails. The entire system lies within a uniform magnetic field. And the bar rail system then forms a loop that's expanding with time, and therefore the area changes. It could also be that the rail moves in the other direction, where then in that case that area is decreasing over time. Regardless, it's two parallel rails, it's got a conducting bar between them, a load over here, and this bar can be moved back and forth. Now, as this bar moves along then, it experiences a changing magnetic flux, which induces an EMF in the loop. This induced EMF will be given by the formula here. The key forces in this situation are that the rod moves because there's a force being applied to it, pulling it sideways. That's where we get this velocity here, which would be a constant velocity because we have a magnetic force that opposes that pulling force. It's common to be asked about the induced EMF in that loop, the direction of the current through the resistor on this side. If it's moving, if the bar is moving from right to left, in that case by right-hand rule, the current would be moving in the opposite direction as pictured here. Could also ask about the magnitude of the force needed to keep that rod moving at a constant velocity. We could ask about the power dissipated by the resistor. We could ask about the current in it and all of that. Sounds kind of nasty, but each of these questions really is kind of simple. And we will look at examples of this type of problem and others in the next video. We'll see you in class.